So, everybody, let's resume our activities. And it's my pleasure to introduce Professor Leonardo Câmara from Universidade Federal do Espírito Santo. He's going to talk about some aspects of function-germs on the plane. Please.
Thank you, Alexandre. So, first I would like to thank the organizers for the invitation. It's always a great pleasure to be here in this workshop with so kind people. And it's also very glad to be back to IMPA, where I obtained my PhD. So today, I'm going to talk about works with the following collaborators: Bruno Escardua, Maria Aparecida Soares Ruas, and Adam Parauzinski. I hope I have time to report about this subject. This is a work in progress. The other two are on the way. So I begin with the concept of Lipschitz, strong Lipschitz equivalence of analytic germs. So you used to say that two germs of homomorphic functions are strongly by Lipschitz equivalent if they satisfy this relationship. That is, there is a Lipschitz vector field satisfying this relation. So another probably more dynamical way to express this is to define this vector field in Rn+1 and states that this relationship is satisfied. So in some sense, the functions are embedded in the flow of this vector field. So this is why this is called strong, because we have a family. So given a family of functions like this, then the associated cool vector field is defined in this way. So if you look to the second characterization, okay. So Kuhl proved the following theorem in 1969. He was trying to study the behavior of germs of functions, or in fact families, homogeneous families in the C0 class. And what he in fact proved is that the Kuhl vector field associated to homogeneous polynomial families are in fact Lipschitz. So in particular, he proved that this kind of structure is strongly by Lipschitz trivial. But he was not interested in by Lipschitz equivalence at that time, in fact. It was a corollary. So we say that, now let's take a look in the holomorphic equivalence, because my first goal in this talk is to answer a question that Alexandre made some time ago. He asked me to understand what is the relationship between these two moduli, the Lipschitz and the analytic for families. And well, at that time I was not able to answer. So we have this theorem explaining what is the relationship of two germs, analytic germs, the classification, the analytic moduli space of homomorphic analytic germs. So this is the symmetric space of the any products of P1s, and you get rid of the generalized diagonal. So you may ask yourself, where did this come from? This comes from the resolution of singularities. So if you look to this family here, and you blow it up, then you shall have, this represents the monofibers of these guys. So you have points here. And these points represents the slope of the homogeneous polynomial. So you shall have something like this, a product of y minus lambda jx, y from 1 to n. And this, since you are interested in reduced polynomials, these lambda j's are distinct if I and j are different. So these lambdas, in some sense, they appear here. So this is the reason why this Riemann sphere with any points, these any points are related to the branches of the homogeneous polynomial. And so this is the relation established between them, because if you have equivalence of another singularity like this, then it's lifted to the blow up, in this case, to the universal bundle. So I forgot the name for this. They're blowing up. So you have this, you have the Hopf bundle here, and you can lift any conjugacy. So if you have another homogeneous polynomial and you have a conjugacy here, then this is the blowing up with this. Then you have another conjugacy here. So this can be lifted analytically. So you can interpret the slopes of these lines as points in the Riemann sphere. So, and its terminology, M, stands for Teichmüller spaces. So I preserve this terminology here. So the Lipschitz type, due to Kuhl's theorem, is determined by the number of branches. And the analytic type is determined by this invariant here. So, but this is very complicated to explain. The action is a little bit complicated, space, symmetric space, and so on. So I would like to simplify this a little bit more in order to understand this in a better way. Essentially, what we are going to do is to build normal forms for these guys. So the first step is to recall the holomorphic automorphisms of C star. And then we have this lemma showing that these two guys are equivalent. They are isomorphic. The idea of the proof is simple. You use a homography and pick the points which are in 0 or infinity if there are any. So if there is some. So you pick them, you get rid of this problem. So you have if you have a representative here, you may have an equivalent one here. So in C star, any lambda j are in C star. And the next step is just to observe that each homography preserving C stars of this form. Okay, so classical complex analysis. So after we reduce this space, and the idea is behind all this is very simple. You have orbits in space of the action of a Lie group, and you try to find a transversal section and work within this transversal section in the group which appears when you reduce the global group to this transversal section. That's the idea behind. So in order to simplify this moduli space. So what appears after is that if you consider this, this is Vn, okay? If you consider this subvariate here, then we just look to the action of the rotations and the inversion. You shall see that something similar appears in the other quasi-homogeneous types. So this is more or less to say that your points are C star, and each one of these lambda j's are inside or outside the unitary disk, and you look to them by rotating or inversions. So And now the group is much more simple because you have only rotations here or this symmetry given by the inversion. So the idea is also very simple. So use the previous lemma. If this guy is different, then this guy is different from 0. This stands for the symmetric polynomials, the elementary symmetric polynomials. So this is just the product of the any lambdas. Okay? And you reduced it to this guy in C star. And after you look that these guys preserving this product must be these two Z or of just two kinds, Z, the inversion or roots of unity, because you preserve this product here. Where is it? Here. Okay? So let me show an example. So let's take a look in the Whitney's four moving lines. So in this case, you have 0 or infinity. This is not good for us, so we reduce it by this homography to this situation. 0 goes to -1, infinity to I, 1 is fixed, and t to this guy. Of course, this will work unless t and none of these two guys vanish. So this is what you ask here. So you look to this product, it's different from 0. You take the fourth root of this guy inside, and then you do a reduction to this family. So a normal form. So when you divide this guy, you multiply all these guys here upstairs by these guys. You obtain this list and for a family. And the equivalence is given by symmetries like I told you. And then you can, for instance, order them in the positive orientation, counterclockwise, or it is reversed by the inversion. So it's easy to see that you have a finite group acting in C star. So it's more easy to do. When you put in this normal form, it's more easy to see how they are related to each other. So the point is that with a fixed Lipschitz type, we have moduli, a full space of complex with dimension 1 of possibilities. So we can have, there is no rigidity. You have distinct analytic types with the same Lipschitz type. This does not happens, for instance, in the other types of quasi-homogeneous functions. Let us take a look. Well, for instance, in this case, the C1 equivalence, for the C1 equivalence, we have to take care of some questions. First, let me recall you how we define the blowing up of a map. Now here, K is R or C. So if this is differentiable, differentiable in which sense? For R, if this is differentiable. For C, this is homomorphic. And then this guy is the automorphism, the lifting of phi to automorphism of the tautological bundle, given this way, given by these formulas. And you see that the derivative at 0 appears here. This characterization is given by a guy called Stark. And he proves a little bit, an interesting, I guess, lemma that show that a continuous map, which is k-linear at 0, whose derivative exists in this k-linear at the origin, then you can lift this guy. And the proof is very simple because it's Taylor expansion. Very, very clever solution. So if you try to use this kind of techniques, then and you're considering C1 equivalence, you have to keep in mind that to lift the conjugacy here is a difficult task because you have to preserve homomorphic complex reactions here. You have R4, for instance. So this seems to be a little tricky. Maybe this is not possible. So if you look to derivative in the light of the previous result, if you look to a linear map in R4, and you split it in blocks, you see that these guys preserve complex linear subspaces. If and only if it is linear, this is good because it would be in a nice shape, or antilinear, and this is not good. So we are not sure that if C1 conjugacy will work. This is a work in progress, okay? But we have this result in our case due to Koike and Parozinski that says that if you have two germs, real analytic germs, and suppose that they are C1 equivalent, then this K and this M must coincide, and these two guys are linearly equivalent, Fm and Jm. This is just Taylor theorem. Just look to the expansion and compare the degrees and nothing else. In the real case, this is easy, but in the complex case, it's not so because you are not, you're using a real derivative, so you have to take care. So I guess it's just a calculation to verify this, but I didn't have enough energy to try to do so yet. But, well, now let's go to the other quasi-homogeneous cases. So I would like to remind you that homomorphic functions is said to be quasi-homogeneous if it's written in this form. Most of you know this very well. So, okay, so there is a kind of, the coefficients here are in a kind of line. The exponents, in fact, are in a kind of line with this slope. And so, as a matter of fact, quasi-homogeneous polynomial can be written in this form with P and Q prime and all these relations satisfied. Okay? In general, we say that this polynomial is commute if this M and K are 0. Okay? So what I mean with this splitting is that this lambda j will play the same as these guys for the resolution of that object. So there is a geometry behind, a complex geometry behind, given by the resolution of singularities. Okay? So we have a splitting. The first type is the homogeneous, and we already dealt with this case. The second case, we call it type 2, and the third one, type 3. So there is a difference. And this difference of shape, well, okay, it's not time to talk about that. I'll explain this after. So there is this stratification. So take a look, now let's take a look in the new future. Well, we say that two function germs are by Lipschitz equivalents. So by Lipschitz, all equivalents I'm considering here are the so-called R equivalences, okay? So they are by Lipschitz equivalent if there is a germ from C2 to C2 or R2 in the real case, such that this condition is satisfied, the usual. So if you go back to that expressions, that factorizations, and you look to the polars of this quasi-homogeneous map, they are written in this form, okay? In case P is equal to 1, this is the type 2, and this one, they are different. In case P is greater than 1, this is the type 3. And this case are determined by this relationship here. And this relation is important for us through what we are going to see. Okay? So, and the RPZ parameterizations are very simple. As also are any kind of perturbation of these guys. The first jets are in the same way. So when I'm talking about perturbation, I'm thinking about something that whose weighted degree is greater. I will come back to this after, okay? So we have to keep in mind. What? This relationship. Yeah, these sigmas are just symmetric elementary polynomials. I'm sorry. Okay. So when we take derivatives, we obtain these relationships. So in 2003, Henri and Paruzinski introduced by Lipschitz invariant. And this by Lipschitz invariant is defined this way. You pick a polar, and you take the expression of f in terms of policies along this branch, and you consider this first jet. So this H0 in the quasi-homogeneous case is determined by the weights, and this is 0 or not. So this is the invariance which we are consider along this work, okay? So in the two cases above, this expression is written in this form for this first branch, which is smooth, when p is greater than 1, and this other expression for the non-smooth branches of the polar. And we obtain this. So when you are in the p equal to 1 case, this guy simply does not exist. So if you look to this expression and we use this, you see that there are the lambdas and the kappas inside. And here are the Henri-Paruzinski invariants, but they are invariants under some action. So I'll try to give you an idea of how this is performed. So back to the analytic classification of quasi-homogeneous but non-homogeneous function germs. The other two cases, the type 2 and 3, I describe it this way. So now it's time to remind the geometry behind. So when you are in case p equal to 1, which you called type 2, the resolution are like this. We have several divisors here, and there is one in which all these branches are resolved altogether. Okay? And in case 3, and you see that there is a corner here. And in case 3, maybe you have a branch here, it depends on M or K, or if it's common or not. So you consider just the common case in order to avoid complications. So then you have things like this. Again, you have a principal branch here, but the difference is that you have another linear chain of projective lines on the other side. So why they are different? Because here we have two corners, so many beautiful colors. And here you have just one corner. So this is the reason why you see this relationship here. The final space stands for this case because you fixed infinity, and so the group of homographies resumes to the final space. And if you fix the infinity and the origin, then there appears the linear group. Okay? So the definition below is the same. Then again, you see that you have different situations. So for this one, you have a marked point, and this is a terminology from Teichmüller spaces, human spheres with any points and an order or marked point. So they are equivalent to this relationship. But to compare the Lipschitz invariance and the analytic invariance, this description is not good. It does not fit. So what you do is a series of reductions, which again means that you are picking quasi-homogeneous functions in obtaining normal forms. So the first one is to pick this guy. The sum of all these lambdas are 0. And when you do that, which appears downstairs the linear group, next you pick another guy inside this one with all the products equal to 1, and then you resume to this guy. So this one is defined here. The sums are 0 and the product is 1. So here the action is given by products of, the action of Zn is given by products by nth roots of unity. So, and finally, you go from the lambdas normalized to the kappas by this relationship. And this allows us to compare the wholes and the kappas and the lambdas, and you see, we are in type 2 in this situation, and you see that, well, I will skip this because this is not much clear, but we are fixing the degree, the weights, and the degree, and so on, okay? So this relationship I showed you leads us to this linear system. This system of equations. So this defines, in fact, up to the symmetries, this defines a covering map. This map here with all these symmetries that appear in one side and the other side, in the target and the source, will generate this relationship here. The invariance given by Ossietzky for this type 2 germs, and here that action, that space we defined above, essentially the kappas sum to be 0. And this is a covering map. This is a completely different situation. Because in the homogeneous case, you're allowed to do a lot of stuff to vary the analytic type. But in the quasi-homogeneous, non-homogeneous type 1, you can't do that. You have to remind that the last blow up here, you have a homogeneous singularity. So the point is that there is a Lipschitz invariant when you try to paste together this guy and this one. In some sense, this answers a question of Anne Pichon about where is the Lipschitz invariance. This is somewhere along the resolution. So when you paste these guys, there is a Lipschitz invariant inside. I don't know how and where, but you have to remind that when you pick a neighborhood of this guy, this will generate by blow down. This will generate a Horn neighborhood downstairs. So this is related in some sense with this canyons and so on, gradient canyons and so on. In some sense, they are related to. I don't know how, but I do believe that this is the case. So you can understand the canyons by blowing up in dimension 2. Okay, the second case is similar. You may imagine how this is performed. Same kind of reductions. Again, you obtain a system, a rational system of equations. And again, you have a covering map. And the different, and you have an upper bound here for the number of leaves of this covering. So there are more things to obtain here, more information to obtain here, things to understand. We understand that a continuous, well, let me state the main result. So if you have a family of quasi-homogeneous and non-homogeneous, quasi-homogeneous function, quasi-homogeneous and non-homogeneous functions. A continuous family, which has, well, it's Lipschitz invariants, for instance, well, but more precisely with Henri Paruzinski invariant constant, then it's rigid, it's analytic. So in particular, it's U1. So they are flat. But for germs, isolated germs, we don't have an answer. We have examples of guys with the same Paruzinski invariants, which are not analytically equivalent. So, but you don't know yet if they are Lipschitz equivalent. So Lipschitz geometry is a little bit tricky. One consequence of this characterization is the following. If you have a family, a continuous family of homomorphic functions with isolated singularities and constant Henri Paruzinski invariants, and such that the quasi-homogeneous part is a non-degenerate family like those that we are studying, then this family is analytically equivalent to one with the quasi-homogeneous part constant. You just have to truncate and observe that this guy, this ft and this p of t, they share the same Henri Paruzinski invariants due to the descriptions I showed you. I showed only in the quasi-homogeneous case, but if you perturb this with higher weighted order, we will change in that parametrization things with higher degree. And the Henri Paruzinski invariants are defined for just for the first jet. So since they share, this, for instance, explain, so the idea is that, isn't it? They share the same, so use this theorem I stated before. Since they are rigid, you may use a family of change of coordinates, not to fix it. In fact, you are just changing these points without changing the analytic type, or those points. And then you obtain this guy. Okay? And this perturbation here has greater weighted order with respect to the powers, to the weights of this polynomial P. Okay. So this, for instance, shows that this kind of theorem by Hernandes and Ruas may ask you, why you fix the quasi-homogeneous type here and let vary this guy to a higher order? I don't want to get in details about this definition, but in some sense this is saying that this guy has an order, weighted order, very bigger than this, but it's softer. So the point is that this observation you already did showed that there's no problem, because that rigidity theorem for quasi-homogeneous functions ensures you that there's no problem in fixing, when you are considering families, continuous families, there's no problem in fixing the quasi-homogeneous type. So this is, in some sense, optimal. So in order to finish, I would like to talk a little bit about the real analytic description of the same objects. Now we are looking to the analytic functions over germs of functions on Rn, and you consider the, just a minute. Oh, I'll talk about this at the end. So you consider the analytic changes of coordinates, germs of coordinates, okay, real analytic. And after that, you consider those with positive orientations. So because it's difficult to do this change in the orientation. So you consider just guys fixing the orientation. And we are, what? Yeah, here are two variables. But in general, yeah. There is some. yeah. This is a general definition, but in what I'm going to talk, I will just consider two variables. In your theorem with Alexandre, you are considering many variables, okay? So I have not to say about n greater than, equal or greater than 3. But for 2, this is, maybe this is the same situation, but you have to do the right blowing ups in the right dimensions for n greater than 3. Well, somebody has to do this calculation. So now coming back to the real analytic case, then we are going to consider functions, real analytic functions, which are right equivalent by germs preserving the orientation. Okay. So again, you have a splitting. We pick the holomorphic splitting. So since you are considering a real analytic function, what happens is that those lambdas appearing here, for instance, or here or there, which are not real, they must be conjugate, because we are considering a real analytic function. So we split this guy in this way. So you pick the modulus here. You have to remind that y and x are real. And if you write this guy in this way, so for instance, again, you have for p equal to 1, you have a decomposition. So the point is that here we have a Riemann sphere, okay, as a basis of the tautological bundle. When you consider the strict transform of the real world, this will become a Möbius band over the unitary circle. So these guys live in this real world, or real transformation of the real world. But these guys, they live in the complex part, but they are conjugate, since everything from the beginning are real analytic. So again, you have a splitting like this, but now we can order, in a lexicographical order, all these guys. So what happens, what I'm trying to tell you, is that if you look to C, we have lambda 1 to lambda n, and they are real. And once you have lambda j here, you have the complex conjugate also in that splitting, because this is real. So you put the lexicographical ordering in these guys here, and you obtain the following stratification. Homogeneous functions, from the complex point of view, they are homogeneous. Quasi-homogeneous of type 2 and quasi-homogeneous of type 3. So, and observe that these guys are real, okay? And if you look to the upper half plane, and you consider the closure of the upper half plane, and also the union of this closure with the infinity, and the compactification of this guy in S2 or P1, if you prefer, or Riemann surface. Also, you consider the affine transformations preserving the orientation so that A is positive. And if you look to this guy, there is a plus missing here, an index plus. Be the linear subgroup of orientation preserving mappings on the real line. So we can obtain the C omega plus equivalence of these real analytic functions. The first case in which you have a holomorphic, complex, homogeneous function. We have this description. In fact, it's almost the same stuff which happens in the complex case, but with the fact that this is there is a symmetry, because this is real and there is a symmetry with this conjugation, the complex conjugate map. There is this guy here. So again, you get rid of the generalized diagonal because you are considering reduced germs. And this guy in the third case, it's essentially the same geometry with only the fact that you have a new symmetry because everything here is real. So the mu's have to be conjugated to each other. So I guess this is all. I only would like to finish, I only like to remark that summing up, well, we used to consider the expression of analytic germs in terms of Taylor expansion. So you look polynomials and so on, and look the germs and polynomials. And this works very well when you have the first jet with the first quasi-homogeneous jet, and I will not explain this in detail, homogeneous. If not, what Isaac Newton is trying to tell us is that you have to consider the first quasi-homogeneous jet. So that thing that you do when you look to the Newton polyhedron or polygon is very important to identify this kind of invariance because of the geometry underlying. So not Taylor, it depends on the steep of these terms of the coefficients different from zero that appear in the expression of this. So what is next? To see what happens when you perturb these polynomials with higher weighted degrees, and this is what we are doing with Adam Parazinski. Thank you.